Neutralization is a type of double replacement reaction. And I can tell this is neutralization because this one is an acid. Its formula starts with H. And anything that's a hydroxide is a base. So acid plus base, this is neutralization. In order to write the products over here, I need to figure out charges on everything here. And just starting with this sulfate, I recognize that it has a -2 charge. And so I could maybe figure out that this hydrogen is +1. It is always +1 for an acid. Okay, and then we go over here, and OH is hydroxide, it's -1, and potassium is +1. And I did that so I could figure out my products. And I'm going to start with my product that's the potassium. It doesn't matter which product you do first, but traditionally we do our salt here. A salt is just an ionic compound with a metal ionic compound, which most have a metal. Anyway, so I've got potassium, and I'm going to put that with sulfate. Since sulfate has a -2 charge, to get a good formula, I need the potassium there, or the 2 there for the potassium. And then my other compound, I take the front part of this one and the back part of that one, which makes it hydrogen hydroxide. Hydrogen with a +1 charge and hydroxide with the -1 charge. Now you may know that this is actually water. This is actually H2O, and this is just a different way to write it. It's very common to write water, HOH, in these acid-base reactions. This is actually a covalent compound. But it's kind of a tradition to do it that way, and you'll see it makes the balancing pretty easy. Okay, then I need some state symbols. And this one I know because potassium is one of the 6 ions that only forms water-soluble compounds, so it's aqueous. And then water, what do you think I would put for water? It wouldn't make sense to say AQ. I'm going to do an L because you can't have water dissolved in water, basically. And so then I need to make sure that it's balanced. And what I noticed right away is the potassium. So I'm going to put a potassium here, or a 2 there for potassium. And then remember that I told you in these reactions, you can treat the polyatomic ions like they're one unit. In other words, this has 2 hydroxide ions. And so I go over here, and just looking at the hydroxide, there's only 1, so I need a 2 there. Okay, and then next I'm going to look at this hydrogen ion. There are 2, and here's my hydrogen ion here, and there are 2. Let's check the sulfate. 1 sulfate, 1 sulfate, and then I'm back to potassium, so now everything is balanced. Well, that is the molecular equation here. I just drew it off the first one. Okay, let's do our net ionic equation. So what's different here is instead of forming a precipitate, we have a covalent compound being formed. And our covalent compound is our water. So I need to show the ions that go into making that. There's a hydrogen ion and a hydroxide ion. And of course, these are aqueous because they were above. And I make sure it's balanced. Even though 2 waters were formed up here, I don't want to say like 2 there and have to have 2s there. You want this to be reduced. Okay, and then this last part. This is a strong acid and a strong base, and anytime you have a strong acid and a strong base, this will be the net ionic equation, basically making water.